first to take a little of the last lecture's geometry, a couple of slides about that. And then we're going to actually solve a real problem, which is an interesting one that if you ever teach physics, you probably want to use this, no matter what method you use to do the theory. The thing that we looked at last time was a mass ratio of 4 to 1 and an initial velocity that was right here, 60 miles an hour. The V1, which is what we'll be calling this axis today, or the V ball, because we're going to use a super ball pen model or experiment, actual real experiment to show the basic ideas. And then the final velocity, which follows the momentum line to this point, if it's a totally elastic collision, came out at 40 miles an hour for the SUV. Tremendous speed is 90 miles an hour for the unfortunate VW. Now, today we'll just work with the momentum lines, the center of momentum, COM line, which is at 45 degrees, locating the center of momentum where these objects would end up if they stuck together. So, if there are any questions about this particular thing, we should maybe ask it now before we go any further.
Can you explain what is the difference between center of momentum and center of mass? I heard here center of momentum.
Wait a minute, speak a little louder because...
What's the difference between center of momentum and center of mass?
Oh, okay. The center of mass is something that occurs in space, okay, in a coordinate space. And indeed, there's a picture in the last lecture of a little scale. I don't know if you noticed that little balance with the SUV and the VW 4 to 1 balance. Okay, and the idea is that that translates into velocity space, and what we're seeing when we have this collision is a balance between the 4 to 1. That's why this line right here has that slope of 4 to 1. So there isn't a connection between the two, but they shouldn't be confused. Here, when we speak of the center of momentum, we speak about a coordinate frame that we would be living in. When we draw it on the graph, well, this is a point in velocity space that we center all of our analysis of a single two-body collision. So center of gravity would be following a curve or a line that if you were to take a movie of the actual motion of the balls or the cars. So that's I think maybe it might help if I showed that picture just briefly here. What I'll do is I'll bring up the text and show you where that is, because that is an interesting feature of this. And I think it's somewhere in this neighborhood. I've got to remember precisely where that is. Let's see if I can find it here. I think it was close to the end of that lecture. That's getting into the next one. So let's go back and see if I can find that. This is, first of all, the wrong file. I need the actual pages unit. So, okay. And let's go find it. should be in this neighborhood somewhere. Thought I had it. In any case, this is a good figure to look at, just to say what it is. This would be the center of gravity for the laboratory Earth frame view. Okay, so it's also the center of momentum, really. The idea is that as these come together, the mechanical system always balances on the center of momentum, or in this case it really is the center of gravity, because if I pick these two up with some sort of crane, right, I'd want to hold it at the center of gravity so they didn't fall one way or the other, right? That's the balance point. So I guess that's the best explanation. Now you go to another frame. This is a good one to take, the center of momentum frame. Then the center of gravity doesn't move, right? It just goes straight up here. Here it has a velocity to the right. Here it has a velocity to the left. Does that make sense?
Yes.
So don't confuse those two ideas, but they're so similar that they're pretty easy to confuse. Center of gravity is a concept that comes up in statics, right? But it also comes up in dynamics. It's just that it's a line of motion that is balancing the actual objects that are flying. Now you've probably seen, and that's something we could make movies of, something complicated like a boomerang or a diver that's actually changing positions as they fly through the air. Okay, if you have a center of gravity, okay, that center of gravity will follow a perfect trajectory, right? Even though the object could be doing all sorts of things. If it's a rigid object, it could be rotating in a very complicated way. But that center of momentum would act as though it was a single particle following the trajectory in the gravity field. So it's a good question, good thing to think about. Okay. Better plug in here or we'll lose our power. All right, now let's get back to this thing. Anything else that you could think of to ask about what we did last time? Okay. This is what we're going to do this time. And it's a project ball with USC. It's funny that Bally came in today and asked me, a problem. And it was a problem we're going to do. So I said, that's a problem from this project. Here it is. Let's demonstrate it. It's something I discovered quite accidentally when the so-called super ball came out. Super ball is just a ball with a high coefficient of restitution, so that if you drop it on anything but a rug, it really comes bouncing up. The rug takes some of the energy, but it isn't enough to destroy this effect. And what I was doing was I was trying to solve a problem which I may give you sometime later. The problem was if a ball is rotating in space and you grab a point of it and hold it, but let everything else move around that point, what is the subsequent motion of that ball? Good qualifying example, okay, that you should worry about solving long before you take the qualifying exam. Good practice when we get to rotations. We can even do it in our review section. But that's what I was doing. I was having a hard time with the problem, so I wanted to do an experiment. I knew the super ball had this frictional effect, which I can't demonstrate on a rug, but basically if I spin it, the thing will go down and bounce and then it'll also balance its rotation. So I wanted to see, you know, where I wanted to see what it would do if it got, you know, because that's what the problem was, is if the ball sticks someplace, what happens. And I was using a pen to indicate where it was. I stuck a pen in the ball, and then I spun the thing a little bit and dropped it. But let's just drop the thing without spinning it. You see, on a rug, it gets it that high. Out in the thing there, it very likely sticks it in the ceiling. And that's what it did in this case. The other thing, it was so fast I didn't see the pen go. I just looked and there was a ball without a pen. And I started cursing and swearing and what the hell's going on here, you know? And a friend down the hall says, "What's the matter, Bill?" And he comes in and says, "What do you have a pen stuck in your ceiling for?" I looked up and there was the pen stuck in the ceiling. I figured, hell with that problem, I want to figure out what this is. This is much more interesting. So that's the beginning of this project. Long before I taught this course, I wanted to know what that was. So what we did was, and this was when I discovered it, I was at the University of California, Irvine. So we went out and we were dropping the thing from higher and higher places in the campus. And all sorts of weird things happen. Usually what happens is the ball blows up. These things are very brittle. So if you drop it from too high, it shatters. And it's kind of like nutty putty. You know, if you take nutty putty and really throw it hard, it'll shatter. Whereas if you just put it on a table, it becomes a pool of liquid. These are all interesting isotropic continuous media problems. But this is a very simple thing. What causes this thing to shoot that pen out? And it wasn't until I got to USC and I had to teach this pre-med physics, this freshman physics course, known for being terribly boring and everybody really hates it. So I wanted to have things that jazz it up, and this was one that I figured would really jazz it up, but I couldn't figure out how it worked. You see, what's going on here that causes it to explode. And the first idea that I had when I saw it happen is that it was a shock wave going through the ball and spitting out the pins, but that's just like saying there's angels inside the ball and then they eject the pin. It is not a physical explanation unless you can put some numbers to it. So I got to thinking about it, and I finally came up with a way to think about it, what we call the it has different names. Independent collision model, ICM, is what we're going to be talking about, because that's the way that we can analyze this very, very easily. But if I had a computer like this right here, and I see if I can get it to let me stick the mouse in here.
I was using your pad.
What's that?
I was using your pad. Oh, here. Okay.
Yeah. I better use this to make it a little easier to draw. But this is, if you go down to when you look at this thing, you got to find all the neat stuff down here at the bottom that explains what's going on, and also has various scenarios. If you just click on this one, this is the one that represents a 10-gram pen and a 70-gram ball. These balls are actually 69 grams, and the pen was a little less. But it's 7-to-1 ratio. Okay? And that is the explanation right there. You see, if you can separate these two collisions, first the collision with the floor, and then the collision with the ball, you've got a model. And that turns out to be a very good model, as we're going to see as we go through this. Now, why is it a good model? That has to do with the nonlinearity of these two balls running into each other, the ball and the pin. But the effect is something that is really hard to get rid of. It's very universal sort of thing that you see in other contexts and don't notice, but in this one you really do notice, and I warn you to be careful with it, because if you do it this way, it can do damage to your eye. Okay, so there's a caveat in the text that says, look out for this, wear goggles if you're doing it with students. And we were pretty, little bit careless at USC. We didn't always wear our goggles. It was long before OSHA would close down a lab if you did something like this. So we didn't get in trouble, and of course no one did themselves. But that's the idea of this whole phenomenon. And the students, the thing that got me started was one of the dental students saying, you know, I want to try to make this. And he actually made a drawbridge out of some magnets he had. This guy was really something. I'd say he's the one that is responsible for making it part of the major project, because you could then drop the a pair or a triple or a quadruple of balls, and then this thing would get out of the way, and we had the whole thing on a very hard floor or an anvil or something like that, and very accurately measure the height of the ball, so we could do a plot of the heights that we got for various instruments of destruction that we were making. It turns out later that this is a model for supernova, a very simple model, way to explain what happens when a supernova collapses. We'll talk about that later on. Really, we'll do it in some detail in Chapter 8. But just this is enough. The idea that it doesn't just explode like a shock wave, it is a two-click collision. It's something that requires that each collision be taken in sequence. And it turns out the most famous Newton, so-called Newton's balls, the string that you buy, and it was a novelty item that was all over the place, and I used to have one in here. I don't know what happened to it. But in any case, for that to work, it has to be independent collisions. Same thing, balls running into each other is a very nonlinear force. I think TC has already found it over there in the heap of things that clutter. If it's not in bad shape, we can demonstrate that. This will...
How about right on top of that laptop?
That would be a good place for it. And so, you know, you guys have seen this, right? The idea that if I take one ball and it pops out the other side, if I take two, or if I take all but one, I get that very nice effect. That doesn't work unless it's independent collisions. And we'll talk about this in Chapter 8 in more detail. But right now, there's enough to do with just analyzing this by geometry. We'll do it by geometry. We'll get the algebra out later on. So that's the main job that I want to get over in this particular lecture, is how to handle the collision. Now, the first part of this, and this is what I want you to do, is take your graph paper and mark it off so you have 8 by 10, so you have plenty of room for 6 inches. That means go from -3 to +3 at least, and leave it, -3 could be at the bottom of the graph. You might as well center it as best you can, and use 1 inch of graph paper, and draw an axis to represent the velocity number 2, which will be the projectile, the pen, and the other axis in the center to be the ball, the heavy object in this collision, or V1. And we'll use subscripts 1 and 2 later on in the lecture, but right now, ball and pen is exactly what we're dealing with here. So we start out with both of these objects falling at some velocity. So whatever that velocity is, at the moment it hits the floor, that's what we're interested in. At the moment it hits the floor, I have a certain velocity which I will call velocity -1. Okay? So that's where we start. Now, the idea, that's what we call bang 1, 0, 1, the initial point that was before the collision with the floor. Okay, this first bang is a floor bounce of M1 off the earth, really, but do it on a very heavy plate or an anvil or something like that. The experiment works well. Even with steel, you could do this, steel ball bearings. But everybody knows what happens to a ball that collides elastically with the floor. And that is, its velocity will change from -1 to +1, or whatever velocity to opposite sign of velocity. So that's the first line to draw on this graph. But we should say a little bit about that, because what we did last time, now use a sort of a blue line here to indicate where things are going, and a little arrow to indicate that we came from the left to right in the velocity space here. But as is seen in the next slide, which I will show on both screens now, mirror reflection through the M2 axis, okay? And that's the first bang off the floor in this little diagram right here. And later we're going to bang off the ceiling, but let's forget about that for now. This is the idea of this little M1 compared to the Earth. Earth is M0, huge mass, monster mass. Okay, that collision would be described by what we've got here, but you would have an ellipse that extended from here to the Gulf of Mexico, and you would be looking at a line that basically went from there to there. Final to initial would basically be what you're seeing right here. Now the Earth recoils a little bit, but we're not going to keep track of that. That's silly to do. But I just want you to be aware that this is a very skinny energy ellipse that we're working with at this moment between the superball and the whole Earth, or the superball and an anvil that weighs several hundred pounds. So that's what I want to, and later on when you collide in M2 or off the ceiling there, M2 will be involved with the Earth. The Earth has a ceiling in an ideal situation. The ceiling isn't a very good one for bouncing off of, but if you did have that, that's what we'd like to talk about for a couple lectures. This back and forth from the floor to the ceiling with a couple of balls. So that ellipse is going to be skinny the other way, but still the actual collisions will be either horizontal or vertical. Now, as I said, the independent bounce models thing makes this work. So the next step here is what I call bang 2. The second bang is M1 versus M2. Ball, heavy ball versus the light pen. So it's a head-on collision now between an SUV and a VW, roughly speaking, except this is a really heavy SUV. This is one that more than satisfies the George Bush thing. It's 7 tons compared to the VW at 1 ton. So what we're going to do is the same thing we did last lecture, is we're going to, first of all, draw a line from this point that has the slope ratio of the two protagonists. That is a ratio that is here drawn with the large mass here, M1 or SUV, and the little mass, I'll just use the lowercase letter here, M2 of the VW. In this case it was 4 to 1. In this case it's 7 to 1. So with your graph paper you can easily count over one something, but always make it the same, and then count that something 7 times. 1, 2, 3, 4, 5, 6, and 7. And then do it again. You can go the other way too. You can go plus with this and minus with that. We go 1 here, positive, and then we go negative 1, 2, 3, and I'll mark there, 4, 5, 6, and 7. Okay, so and I put a little circle around each of these points because I need to draw the momentum conservation line. Then I go 1, out, and then again up 1, 2, 3, 4, 5, 6, and 7. And put a little circle around that. So using all of those circles, and I can check to see if I counted right because they all should be on a straight line of slope minus 7. And it looks pretty good. Okay? So that's our momentum conservation line. It's analogous to the line we drew of 4 to 1 negative slope for the SUV VW collision. Here I'm going to go ahead and draw a faint line through there. So the solution to our collision problem has to be somewhere on this line. Most probably not on this end of it, but somewhere in this region here.
What is the blue line that goes all the way from -1 to +1?
I'll say that again.
But what is the blue line, horizontal line?
Okay, this is what I'm going to use to just map where the ball is and pen system is located in velocity space. It starts here. This is the real initial point. Let's call it initial 0. And then this is, or initial -1, that's where it really is. And then this is the initial point that's analogous to what we did in the last lecture at number 1 point, just below +1. And then the question is, how far up this line does it get? You see. Well, we need to work with this VCOM object here. Okay? Remember, VCOM, for an elastic collision, is the average of the velocities associated with this here. And I should say it's the vector average of the vector V n, that's this guy, and divided by 2 sum with V fin. Okay, so means we got to draw a circle after we find out where the COM is, and that's easily drawn. And we'll need a 45-degree line extending at least to +1, maybe a little past that, so let's just draw it all the way across this graph. Whoop. You've got gravity to worry about. You've got a horizontal surface, so it's less chance your ruler slips. Let's start again here. So I'm going to go through that point right there. My chalk is getting a little fat here, so I having trouble maintaining the line, but that's a pretty good 45-degree line for conserving momentum in this particular graph. Okay? So go ahead and put that on the graph paper, and you already have marks that are very precise, so it's easy to draw the lines of a given slope, in this case slope 1. Okay, circle. It starts from that center of momentum point. Okay, so this is the VCOM. I'll just write COM there, because we're going to have other curves, other lines going on this graph as we try different parameters. But let's just get this one done first. Here is the center of momentum. Put this thing as close as I can to there. Set my compass to draw an arc through the initial velocity. Okay? So I'll tighten it up and hope that it will remain. So I'm going to have, and I'll just draw the whole circle so you can see where it's going. Up, up, up goes. And there it goes right through there. Okay? Now you have much more precise graph paper and less clumsy compasses and rulers that we do here. But from the looks of it, I am actually hitting one of the dots that I put on there. Looks like I'm about 2.5, maybe a little less, 2.489 or something like that. It seems to be just a little below there. I know from a fact that that's wrong. It is in fact 2.5. And then this one right here, where that hits, is very close to 0.5. So that is our velocity amplification factor for 7 to 1, right there, 2.5. 6.25 is a square. Right? That's an indication of how much higher this thing goes than what I drop it. That's a whole nother issue, gravity. We're bringing that in. I'm assuming you know enough about the distance and height ratio, velocity ratio that would give you that. Now, this, is a very simple way to get an answer to why does this thing fly like that. And we're going to do some more with it. But what I would like to do before we continue with that particular mass ratio, solve a problem, and this is the problem that Valley actually showed me just a few minutes ago, and that is where and what ratio, what slope would you want to try so that you take all of the energy out of the big mass, out of M1, and put it into M2. That's an interesting problem. Now, other problem that might have been asked first is if I make the pen lighter and lighter, use smaller and smaller masses. Right now I'm using 1/7 of a super ball. What if I use a 10th or a 20th or a 50th or, a little particle of dust? Is a little particle of dust going to come out like a particle accelerator and go through my brain? I mean, we got to be careful with this thing. I've obviously almost put out my eye doing this experiment the first time. Let's not, get in trouble with something that's even lighter. So what this lets you do, this geometry lets you do, without looking at any equations at all, you can just psych this out and you can say to yourself, okay, got a ruler here, it's going on that line, okay? What would it be if I just started walking my ruler around to higher and higher slopes? That means bigger and bigger ratios, m1 to m pen, as m pen approaches 0, finally the slope approaches infinity, right? So if I'm talking about, just a tiny little flake of a sand grain or something like that, it'd probably be something like that, right? Well, if I put my compass here and draw from there, I don't even need to draw it. I can see, but let's go ahead and do it because it's kind of fun to see that too. If my compass gets put somewhere in this neighborhood, I draw a bigger circle, okay? And you can see how it compares with the other circle. This is the one for infinity, or nearly infinity. And the answer is 3. That's the absolute limit to the velocity amplification that I can get with this system.
How do you get?
I don't have to worry about the fact that I'm going to create the Hadron Collider in this room by using very small pieces of sand. Okay?
So why do you stop at that, Dr. Harter? Like,
Because that's the slope that I would be approaching. This thing right here would be slope 1 to 7, right?
yeah.
1 over 7, okay? This is, right here, slope 1 over infinity, okay?
How over here? No, this way.
Right.
He shifted again and accidentally.
Oh, I'm looking at the wrong,
The vertical line.
yes, I should be right here, right? Here, yeah, okay? This would be slope, and this was actually a slope of minus, but let's forget about that. This is lazy 8, right? So there's 1/7, there's infinite, right? Okay? So these are the two solutions that we have so far here. Now, it's, worthwhile experimenting. If I were to pick, some other slope, what's available here with the graph that I have that's easy to pick on, what do I got if I do a ratio of, say, this distance here to there. Let's go all the way down to here because that's where the line's going to originate. So I would be talking about 1 unit to 1, 2, 3, 4 times 4, 16. Okay? If I draw a line from here over 1 and then up 4 times 4 is 16, I go right through this point here, right? So there is what I would get if I had a pen that was 1/16 the mass of that super ball. So let's go ahead and put that one on the graph, but you can pick anything you want in between that, and what I'm trying to show here will be fairly obvious. And this is one of the first theorems of geometry, the theorem called the pencil theorem, that we're going to be deriving here and using. There are all these old theorems. Okay. Now I'm going to get out the compass and work that particular center of momentum. The center of momentum, of course, is moved over. So the 1/16 center of momentum is now right here. This is the infinite one right there. I need to use that with my compass to figure out.
So how did you line that? How did you draw that line in the middle, Dr. Harter?
This line that I just drew,
Huh?
it's pivoting there,
Right.
okay? I want it to be a slope of whatever this is to whatever that is. Well, this is 1, and then the other one is 1, 2, 3, 4, 5, 6,
7.
7, 8. You see what I'm going? 9, 10, 11, 12, 13, 14, 15, 16. So this is slope 1/16, right?
So,
I should say it's 16 over 1. Yeah, I always get mixed up whether I'm doing slope this way or slope that way.
why do we need slope 1 by 16?
Well, the slope of these lines is m1 over m2.
Right, yeah.
It's choice. He
Yeah.
chooses this one.
I just picked it because I have a nice mark here to refer off of.
Oh, okay, so you're just choosing that ratio.
Yeah, this is sort of halfway between what these two.
Oh, okay, so you want to choose a point halfway between 1
Yeah,
over 7 and
roughly.
1 over infinite.
Yeah.
I mean infinity.
Yeah,
Okay.
right. So that's a nice one. Slope 16. Okay. And I should take that 1 off and just do what it is. This is -7. This is -16. And that's minus infinity right there. Okay? And while we're at it, wouldn't hurt to draw another one. Say a line that went through that point right there. That's talking, there we're talking about a slope of 1 to 4. Okay? So that's less than the 1 to 7, or more than the ratio 1 to 7, but the actual ratio m1 over m2 is 4 for this one. Okay? So I'll go ahead and draw that one too. And go ahead and draw the circle that goes with that one. That particular ratio hits right here. That's our center momentum point for the 4 to 1 ratio. Okay, so this is slope -4. Slope -7, slope -16, and slope -infinity are all there roughly equally spaced. And the circle for this one is a little smaller than the others. So here's the 4 circle progressing its way up to the answer, hopefully. So I don't slip here too much. Okay, and that looks like 2.2 or something like that is the speed that I'm getting out of that one. Okay, and let's go ahead and finish this one. Also, I forgot I had drawn the circle that goes with this particular fellow. 16 to 1. If I don't slip, should be able to get up there. Just slip a little bit there. So there's 4 answers to this problem for different mass ratios. See a trend? See a nice linear trend? I'll use some green chalk here to indicate the locus of all of the velocity points for different mass ratios. Oh my goodness. I think I ought to use a red piece of chalk because this is parallel to this, right? Very definitely parallel to that. These points all lie on this one. We can go ahead and take it right down into this region too. But we have to discuss what actually happens when you make the ball on top bigger than the ball on bottom for a collision like the one we're doing. And in the process, we solve Baldy's problem. You see your solution there? Your problem was, what mass ratio
Yeah.
do I need to get rid of all of the velocity in ball 1?
Yeah, that's 0. So that makes it.
And what's the velocity that you get?
Yeah, that's 2. That's what I got.
You get 2. You're right.
And mass
Now
ratio.
let's go ahead and finish it. What's the mass ratio?
I got 1/3 when I did.
1,
Right.
and then 1, 2, 3, right?
Yeah, 1/3.
So that's a really interesting solution, obviously. Very relevant. And interesting that I get the number 3, which is the number that I associate with mass velocity, the gain in the velocity ratio, 3 to 1, is our limiting case for infinity. Here is the ratio of the masses, that's 3, that winds us up at the optimum energy transfer line. I'll go ahead and extend here, but I don't really need it. Actually, the chalk isn't even drawing it. I think that's good enough. Okay? So there's a slope minus 3. Right next to slope minus 4. Then there's a gap before we get to minus 7. So there are the solutions that I want to discuss for this object. Now, of course, we can drop off to have a slope 1, minus 1 actually, for equal masses, and that would be the Newton experiment. We'll talk about that later on.
Dr. Harter,
This
what's
is
the-
enough to give you a feeling for...
How do we calculate the mass ratio? I mean, I'm able to infer how to calculate the velocity. If v1 is 0, then v2 is 2 times v.
Well, you simply read it off the graph. There's V2, the coordinate for V2 right there, right? And then there's the coordinate for V1,
Right.
there, and then there, and then there. Obviously, it didn't change at all for a tiny little specking mass, right? The infinite mass, the ball doesn't even know there was anything on top of it. Right? That makes sense. Now, of course, you might ask, well, what goes on the other side here? Negative mass? Yeah, might be. But let's not get too far off the track right now. We'll worry about those kind of things when we get some time at the end of the course in Unit 8 with relativity. This will give us enough food for thought right here. Now, what happened here that's very interesting to a geometer?
Dr. Harter, just one question. The slope of the line that passes from the initial point through 2, that is 2 on the y-axis, has a slope 1/3, right? That which gives us
This
a mass.
particular,
Yeah.
this last
Yeah.
one.
Yeah. So
has
that's a mass ratio.
Yes, that's right. Yeah, this ratio, the ratio of this to this, actually it's this to this when you speak of slope the way you're used to doing it. Now remember I called the actual geometry of this construction the pencil theorem? here's the point of a pencil here. See the pencil? Pencils used to look like that because you sharpen them with a knife, right? There'd be little grooves in them, right?
Yeah.
And you know the lead would stick out right here if you sharpened it really well. Okay, so there's the pencil. The theorem is that a pencil of lines intersecting two parallel lines at any angle, not just 45 degrees like this, maintain the ratio. The ratio of this to this is going to be the same for the pencil, no matter how big it is. This pencil could be really fat, go from, you know, here to there, right? It's still going to cut these two red lines with precisely the ratio that you see here, namely 1 to 1. This ratio is 1 to 1. If we were demanding a lesser ratio because we didn't have quite the pure loss of energy, no loss of energy, perfectly elastic, is what we give us a 1 to 1. But if some other ratio were to come up, then a line further down would be useful too. Energy loss doesn't always work out that nicely, but it could, and then you would be able to use that too. But that's the pencil theorem. So once I drew this right here, I knew all I had to do is drop 45 from there, and that's going to be my solutions, if this is where the center has to be from this particular point. So that makes the geometry really easy. But I did it in the way that you sort of usually solve for geometry these days. You just try it until you see a pattern. That's what makes geometry powerful. Now, I already mentioned to you about the ellipses and the ratios and things like that. That's all happening here each time we change this, and we're going to look at that too. But this is a pretty neat picture of the, let's come over here and just look at the pencil lines that I've got going right here. I showed a 2 to 1 here, a 3 to 1, and then this thing right there, which is, we didn't have one of those. Yes, we did. This is the 4 to 1 right here. Yes, I've got it labeled here. And 7 to 1, and then 15 to 1. A little bit different from our 16 to 1. Okay? That makes sense. I think it makes more sense than solving quadratic equations over and over again for each of these results, which is what we did in that paper. We weren't that smart. That paper doesn't have this geometry in it. Really should have. It would have been nice, but wasn't available. Didn't think that far ahead. Okay?
And they don't have it in the library.
Now, one of the things I'd like you to do is take the data from a system like this, and we'll just keep the mass ratio fixed, and use the various velocities that we're going to get. In particular, the next stop for this one, and this is why I'm going to use the blue again, because we're talking about the 7 to 1 solution. So that's this one right here. So let me outline that one in this color that we started with.